online version of the ESIG Tucson Spring Technical Workshop. I'm Charlie Smith, the Executive Director of ESIG, and I'll provide a few brief opening remarks. As you know, we canceled the physical meeting in Tucson due to the coronavirus situation, and we decided to proceed with a shortened online version. Today, we're holding the last of 12 sessions which started in the middle of March. Recognizing the limitations of a webinar with typically a few hundred people on the line, we'll have individual presentations of 10 to 15 minutes, followed by a minute or two of discussion, moderated by the session chair, with hopefully some time for discussion at the end. The lines will be muted, so we have to use the question box in the lower right-hand corner of your screen. Today, we'll be hosting the closing plenary session, Nuclear and Renewables, a match made in heaven or hell, chaired by Mark O'Malley. Mark is a professor at UC Dublin, returning from a recent sabbatical at NREL, where he was the chief scientist for energy systems integration. During his previous time at UC Dublin, he led the world-renowned Electricity Research Center. Mark has too many accolades to mention, although I think that one of which he is the most proud is his invitation to membership in the U.S. National Academy of Engineering. His current research interests lie broadly in the field of energy systems integration, as exhibited by his current leadership role in the Global Power Systems Transformation Initiative. I've known Mark for many years, initially through our collaboration with the IEA Wind Task 25 on wind integration, and subsequently through participation in ESIG activities, where he chairs the Research and Education Working Group. Mark is a good friend and a good friend of ESIG. Mark, we appreciate having you here. Turn it over to you.
Okay, thank you, Charlie. Just for his information, Charlie went far too long on my bio there. I will not go as long on the bios of the speakers, I'd have to say, for time reasons. So the title of this is Nuclear Renewables, a match made in heaven or hell. Just very quickly, how this has come about is that for decarbonization, nuclear and renewables are probably the two technologies that we can do it with. And the question is do they work well together or do they not? And there's some debate about that. So we've put together 5 speakers today who I think will be able to shine some light on this issue. So without further ado, we'll introduce our first speaker, John Reilly from MIT. So John is the co-director of the Joint Program and senior lecturer in the Sloan School of Management. He's an energy, environmental and agricultural economist. Each of his interests are in integration models in the global economy. He's also served some time at the U.S. Department of Agriculture, PNNL, and the Institute of Energy Analysis, Oak Ridge Associate Universities. He's got a PhD and an MS from University of Pennsylvania and a BS from the University of Wisconsin. Okay, John, the floor is yours. I think the title you put down here is the size of the problem, so I think John will give us some illustrations of how big this issue is. John?
Thanks much. It's a pleasure to join all of you today virtually. So this is some work that I did with colleagues here, Karen Tapiahumada, May Yuan, and Ken Stresbach. It's a model of the U.S. electricity sector resolved at an hourly level. So we started this out to look at, was nuclear necessary for deep decarbonization? But we realized that in order to kind of think about whether nuclear is necessary, we had to understand or better model the role of renewables. Because at the point, of course, renewables, at least on a levelized cost basis, look much less expensive than nuclear. So why would you even bother with nuclear? So let's see, I get used to proving these. So this is just that story, whether you look at amounts of power generation going in, it's all heavily focused on, the investment is all heavily focused on wind and solar. The Energy Information Administration has wind and solar at 5 and 5.3 cents per kilowatt hour, and nearly competitive with natural gas, even without tax subsidies. Of course, we hear in some places that it may even be cheaper than natural gas in some locations. Whereas advanced nuclear in the EIA thing has it up around 7.6 to 8.4 cents per kilowatt hour. So, it doesn't look like there's even a reason to consider nuclear in that given those costs. Of course, you all are aware that, the renewable aspect of the intermittency of renewables adds some additional costs that aren't captured in a levelized cost basis. So very quickly, there are a range of different electricity modeling levels, from capacity planning down to protection, stability of the system, load flow. We focus, the model we have doesn't get into stability and load flow. We're just looking at, but we're combining capacity planning and down to economic dispatch. So that's just a little thing about the model. There's another little slide on the model. It's determined. It's a cost minimization LP model that chooses the least cost options to build out as things retire, and you need to build more. And then once the stuff is built, it dispatches the best. There's various ramping limits on technologies. So one of the things, of course, is that nuclear is inflexible. So we have, in the base case, some limits on what you can do with that in terms of nuclear flexibility. So I'm not going to go into a whole bunch of the model. Hopefully, I had on the front page or somewhere a list to a reference to the paper if you want to go look at it. If not, you can ask me. I'll send it to you later. So the scenarios we ran with this model was a reference with technology costs starting at, we used mostly EIA costs, but wind and solar, we wanted to make sure they were declining, that we're not disfavoring them. And of course, their advance has been fairly rapid. So we have them declining at cost at 3% per year, reaching a little at $30 to $50 a megawatt hour, where nuclear is at $94 per megawatt hour, the EIA current cost. We do a cap. The rest of the scenarios all have a carbon cap, reducing CO2 emissions in the electricity sector by 90% from 2005, with the base technology assumptions there. Or then we have a low nuclear cost case where we drop it to 55 to 60 dollars per megawatt hour. Again, still considerably more expensive than the renewables, at least at a levelized cost basis. And then we remove the limits on nuclear ramping up and allow it to ramp up and shut down easily. So a flexible nuclear case to test whether with greater flexibility, you could get more renewables and nuclear could play the flex role when it wasn't there. We also have, some pumped hydro storage ability that can work during the day, but we limit it to being charged or discharged in one day. You can also spill the renewables, so you can just build more renewables in different places and spill them. We've used a base NREL map of what renewable variability is for the country, for different regions of the country. So to get to the scenarios, this is, I think, the key scenario here. And so if you start on the very left, you see that is the generation from different sources in the reference case. And you see in the reference case, the green and blue on top are wind and solar. And you see that they're expanding, continue to expand through that period, even without any additional carbon cap, because they are at the cost assumptions gradually getting less expensive than any other option on a levelized cost basis. The next, and this is going from 2016 to 2050. The next group over, that's with the cap case. And there you see wind and solar expand even more. We're achieving the cap. You will see on the bottom, the bars pointing down below, that we are getting a fair amount of spillage of just wind and solar being produced when there's no demand for it. The next one over, we lower the cost of nuclear to that 55 cents per kilowatt hour, $55 per megawatt hour. And now all of a sudden that changes the picture pretty dramatically. We have a big expansion of nuclear. We still have wind and solar reaching about the same level it reached in the reference case, and so it is contributing to decarbonization, But once you get into that higher level, about 40%, we don't see it expanding much after that. We go out to the next one to the right, and that's where we increase the flexibility of nuclear. And you see almost no difference. So between that and the previous one. So our story is that nuclear flexibility, technical flexibility, doesn't mean you use any more of it. You don't want to build nuclear power and have it sitting around not operating 95% of the time at a fairly high cost. So instead of using it to increase, to complement wind and solar, you just don't build the wind and solar and build the nuclear instead. And so as a result, it doesn't really need the flexibility because you build it to run all the time. Now, I think a caveat here is we went to 90% emissions reduction. If you go to studies that are trying to go out to 99, 90, 100, then you start asking, what do we do with the natural gas and the peaking sort of thing? So there may be more of an issue there. And this is just showing what's happening with, again, we didn't show, this is showing just the flexible nuclear. The low-cost nuclear is the same picture, essentially. But what you're seeing is that we are, in that cap case, when we're relying more on wind and solar, we're building a lot more capacity. And that just reflects that a lot of it is being built and spilled. That's cheaper than a lot of pumped hydro storage or the expensive nuclear in that case. So that's kind of the trade-off there. What's the relative cost of nuclear and renewables? Nuclear doesn't have to be as cheap as renewables on a levelized cost basis, but it can't be as expensive as it is now. So and then what does that do? Well, this is a carbon cap. So we have carbon prices. You see the benefit of having that low-cost nuclear. Well, without that and just the renewables, you see the carbon cost rising up to almost $150 by the end of by 2050. So it just becomes ever more expensive to find ways to produce power or have enough power when you need it, when you don't have a dispatchable power source. But if we add in the low-cost nuclear, then we get the cost of that carbon price dropping by 70%. And you see the flexible nuclear is a little bit cheaper than inflexible nuclear. So there's a little bit of an advantage to flexing it, but not much, at least going out to 90% drop. Now, if we did begin to see more, if we wanted to go to 100, maybe then you would get something. But I think then you have to ask, could you get something like biogas, carbon-free, carbon neutral, biogas or something coming in? So that would be the other thing to look at. So I think variable nuclear, match made in heaven. Well, there is no match. I think they're mostly substitutes. The nuclear technical flexibility was largely irrelevant. We talk about economic flexibility, and you don't want to flex nuclear from an economic standpoint. So that seems to be more important than technical flexibility. I think there are three basic possibilities here. Nuclear is too expensive and completely out of the picture. Nuclear is more expensive than renewables, but less costly than adding storage or spilling renewables. So that's when you get both. Or if it were really cheap and less expensive than the renewables, then why would you build any of them? I think the caveats, where the boundaries are, between these three cases, depend on the relative cost. We haven't pushed this near 100% carbon reduction, so that I think could change the picture a bit. And this is an optimal planning model. There is always the result that if we do an optimal plan, the world never turns out as our optimal plan. Maybe under that situation, there would be some value to having technically flexible nuclear, because you might end up having to flex it in situations you didn't plan for. So I've stopped there, and if there's a quick question or two, I'm happy to take it, but thank you all.
Okay, very good, John. So listen, there's an absolute deluge of questions here, I can assure you. So to everybody, I'm going to take some of these questions will be dealt with later because we are going to talk about flexibility more generally. So I'm going to park those. I'm not ignoring them. But I suppose the first question is one about costs. One of the questions is about the fact that your costs for wind of $30 to $50 it's actually at that range now. I think the implication is that you're taking costs that are actually 2030 costs that you're taking are actually real on the ground now. So can you, is that?
The wind is 3 cents. The 5 was for the solar.
Yeah, but I think the questioner is saying that the numbers that you are saying that would exist by 2030 actually exist now, the cost numbers, particularly if you look at Lazards and people like that. So did you do a case with even lower costs, wind and solar? I think that's basically the question.
No, we didn't. When we were doing that, I mean, I think the costs have been dropping. I think there is question of what the cost is, how subsidies are involved, how things are actually being bid in, and other sorts of things. The exact what the cost is a challenge. I think the key element here is as I said, the relative cost between nuclear and solar. If we drop, or wind, solar, and nuclear, if we drop solar and wind further, if we really think they're going to be a cent a kilowatt hour, and nuclear is then 5 cents a kilowatt hour, that's more like the scenario we have with them at 3 and 5, and nuclear at 9. So it's that relative cost that matters. So yes, if they are much cheaper, then you'll get that picture. Then the picture will look much more like the one where nuclear is at 9.6%, not using any nuclear, just doing all wind and solar, but still facing the need to add storage, other backup, other things in order to make up for the renewables when they're not matching.
Okay, John, there's a lot of questions here, but I'll try and tease one out with you as well. On the storage question, what about, battery? Did you do a direct, you've said it yourself that, there will be this competition between, say, nuclear and batteries. Did you look at any of the numbers around that at all? Or did you just,
we have a storage option. We kind of bid it on pumped hydro storage because that looked cheaper than batteries. But it's a storage option that we assume can only work for the day. So you can store at night and use during the day, or store at noon and use later in the evening, but you can't store for weeks or months. So that's the main way we see batteries working at the moment. So the question is, what is that cost? The cost we have in there, we get some of it, but again, what that's going to be relative to the nuclear will end up being whether if you can store for free, then you don't need nuclear.
Okay, there's a lot of questions here, John. I'll ask one more and then we'll go on. A lot of these questions will be answered by some of the other speakers. If nuclear is to get less expensive, where's the direct, what's going to happen? I think some people want to know if you say here one of the options is that nuclear will get cheaper, but how? Is there any sight of how it will get cheaper?
Yeah, we cited a paper that gave some estimates, and so that the cost we use is actually the middle estimate they get for low-cost nuclear. They imagine this sort of small nuclear reactors that can be built almost on an assembly line, and so instead of building a bespoke nuclear power plant each time, which is completely different, requires all the engineering, you would build it like that. Again, that's an estimate. Whether that's possible or not, obviously you need to scale that whole industry up. So, and we haven't looked at any of the regulatory barriers to possibly that new nuclear technology might face. So there's some big ifs there, obviously.
Okay, that's great. Listen, thanks, John. We'll move on from there. Lots of questions coming in here. I think you can see the questions, John, if you want to deal with them as we go on. Okay, thank you. So Sherry's up next. So Sherry Bernhoft from EPRI is a senior program manager in the Nuclear Innovation Department at EPRI, and she's also she has worked in industry in the actual nuclear industry herself. So I think she's got some really good experience. And she's a chemical engineer from Lafayette College and a master's in business administration from Webster University. Sherry?
Okay, can you hear me okay?
I can. I'm assuming the other 250 people can also, but if not, it's just you and me.
All right, great. We'll have a good conversation. So I'm going to go on the side and say that it's a match made in heaven between renewables and nuclear.
Good.
Yeah, and the reason for that is, if you look at the takeaway on my slide, nuclear power plants were designed for flexible operations. If you go back to the early design documents from Westinghouse and GE back into the 60s and 70s, that's what nuclear power plants were designed to be. And moreover, we do have operating experience that I'll talk about. In the United States, back up until about the mid-1980s, it was very common to use the nuclear power plants for frequency control. They kind of floated on the grid. Now, there were some changes in the Nuclear Regulatory Commission, their rules for control of reactor power, and that kind of set this whole mindset in the United States in place that nuclear power plants aren't flexible. But counter to that, the Columbia plant out in the state of Washington has actually been flexible for decades, and they're used to balance the river flowage on the Columbia River. And then if you go outside of the U.S. and you look at France in particular, but there are other examples in Germany and Belgium, where the plants in France, because they are, the main source on the grid, over 75% of the power on the grid comes from nuclear. The 58 reactors there for over 30 years have been very flexible. In fact, they move between 20 and 100% power within 30 minutes, and they can do that up to twice a day, and they are controlled for load following. They're also used for primary and secondary frequency control. Now, the caveat I'm going to add for everybody that's getting excited about that is that the French plants, they were designed with what we call a gray control rod, and that gives them some ability with controlling the nuclear reaction. And if you want to go into that, I can go into that, but I don't think that's the purpose of today's talk, but I'm happy to answer questions on how that happens. So let's talk a little closer in the U.S. and some more recent experience. As renewables started coming on, a number of our EPRI members in the U.S. in particular, and also in other countries, started coming to us because what they were experiencing was this periods of negative prices. And so we started a research program. So since the early 1980s, people haven't been operating flexibly in the U.S. and some of the other countries around the world, and they've kind of gotten used to being baseload plants. So we put together a research program. We wanted to assess the long-term impacts on the fuel and the plants and help develop some proactive strategies as we moved into flexible operations. And we went at it with a phased approach. And this started in 2013. Since then, over 20% of the plants in the U.S. right now are operating flexibly in some range. And I've hit some of the highlights here. Excel participates in a day-ahead market, and they're operating between 70 and 100% power. Exelon does what they call advanced nuclear dispatch, and they're in that same range. And you can see the ramp rates on theirs, and I can show you in the next slide some data that we have from Exelon. The Columbia plant I talked about earlier, they do ramp between 70 and 100% power, and in the spring they also do periods of extended low power operation, particularly during the snow melts, to manage that. The Bruce plants just north of the border up in Canada, the CANDU reactors are designed that they can bypass steam to the condensers, and they do quite a bit of maneuvering. As you recall, Canada has shut down their coal plants. So again, the base on the grid that is providing that flexibility is the CANDU nuclear reactors up there in Canada. We've also been working with Belgium and Spain, and I can also say that there are several other plants in the United States that are actively evaluating their options for flexible operations. And the reason for that is the negative electricity prices, the grid congestion, but moreover, it's the positive interaction of the relationship between renewables and nuclear power on the grid. It's not one versus the other. It's how can you work together to ensure grid stability, economic dispatch, and a low carbon footprint. So with that, we've been working, like I said, quite closely with our members. collecting the lessons learned as they've been operating since about 2013 flexibly. The picture you see there, that is provided by Exelon for one of their PWRs. That's following economic dispatch over a 7-week period. That would be the spring in response to the wind generation on the grid. So what we found is it is very important, and this happens, that the plant operator does maintain the reactor in a safe operating window. The training for the plant staff, especially the operations crew, is critical. Chemistry of the plant does need to be monitored on a more frequent basis. For your pressurized water reactors, there is going to be some increase in water usage. So you have to look at your storage capacity on the plants and the amount of chemicals that you would use. We've gone through and we've looked at, for some of the critical components, what the inspection frequencies and maintenance intervals would be. In some cases, those do need to be adjusted. When you look at the secondary side of the plant where you have the steam flow coming through, you do get some increased or some changes in the wear rates for the secondary piping based on the changes in the steam flows. We need to evaluate maintenance practices, means the plants are moving up and down some. It does put some additional wear and tear or some increased maintenance activities, especially like on some of the pumps, the small bore piping, valve packings, those type of situations. And you need to be walking down the plant, be a little more vigilant, because we learned this first from the coal plants and the gas plants, which do quite a bit of flexing. A lot of your plant impacts and what you see happening are going to be what we call latent, meaning it won't happen right then when you cycle the plant, but it could be an accumulation of cycles that will start to cause some of the issues or some of the things that you need to take care of from a plant standpoint. But overall, the plants are managing the flexible operations, and it is being successful. And again, it's being well used to manage periods of negative pricing and grid congestion on the grid to allow the renewables. The one thing that is important, when you're looking at this from a grid operations standpoint, is it's not like a coal plant. I'll say that right now. At least in the United States and several other countries, Spain in particular is one that we're working with. Only a licensed reactor operator can change the power level. So what that means is that there needs to be a close coordination between the grid operator and the nuclear power plant control room. And what we've found is that you want to have this well-defined up front so that there's a good understanding of the rate, the depth, the duration, and the frequency and the time and core life, which are all tied to the core physics, so that the grid operator knows when they can contact the control room, and the control room has a safe envelope in which they can maneuver the plant. This is all defined up front through these protocols. And it also needs to be clear that any time that the plant management can opt out of flexible operations. For example, if they do have other activities that are happening in the plant that do take their full their full attention, and there are certain tests that you need to do on a routine basis, like a core calometric, where you do need to have stable reactor power conditions in order to complete those tests. But other than that, with the protocols, things are working very well. And we're looking towards the future with our research program on how we're going to optimize the flexible operations. We have some pilot studies going on right now on trying to quantify what the cost of the flexible operations is being. We know the benefits and the value that it's giving. What we're trying to do now is quantify, what is it costing the plant with regard to maybe some extra chemical usage or some extra maintenance frequencies. We're also working on, for the plants that have been base load for a long time, how we can help them expand their range of flexibility. What plant modifications or changes would be needed to start approaching power levels as low as 30%, similar to what they do now in France. We also have a study going on working with our power distribution group on grid services. Eric Ela, if he's on the phone, could do a lot better job explaining than I could some of the restrictions that FERC has right now on the primary frequency control from nuclear power plants. But we are working with him between our nuclear area and Eric's area on what is needed to look at primary frequency control from nuclear power plants as a grid service that could be offered. And then we're also working on an area that Bethany is going to get into a little bit more after me, and that is what else can be done with the nuclear power plants. Can we look at, instead of cycling the reactor up and down, can we look at using that energy for thermal storage, water desalination, or hydrogen generation? This is an example. Again, Bethany's going to go into this a little bit more. I can look at it from the operational standpoint. She'll look at this from the economic standpoint. But if we have, say, 30%, if the plant's operating between 70 and 100% power, that's 300 megawatts. If a typical nuclear power plant is 1,000 megawatts, you have 300 megawatts. Can you use that in a hydrogen electrolyzer to produce hydrogen? The advantage is with the steam electrolysis, there's no carbon produced there, and you're using a no carbon production or emitting source from the nuclear power plant. So you're producing a low carbon energy carrier that has multiple uses. This is something we're very excited about, and U.S. Department of Energy is funding some demonstration projects at some existing nuclear power plants to look at this. And this was also touched on too, what does the future hold? Well, we're very excited, and I think our last presenter today is going to talk a lot more about the small modular reactors and some of the advanced reactors, and how by looking at it right from the start as you're designing the plant, the opportunity to be much more flexible. The other advantage that the small modular reactors and the more advanced reactors are providing also is that they're going to have much higher steam output temperature. To produce something like hydrogen today, we do need to boost those steam temperatures some more. It's still a good thing to do. The demonstration projects that are going on will be very useful to look at the economics and the logistics of producing hydrogen from the existing nuclear power plants. But as you start talking about some of the advanced plants that are, the next generation, you can see that the type of temperatures you get, you can directly convert using the steam with high temperature electrolysis, which is a lot more efficient to produce hydrogen, pneumonia, or other alternate type of materials. And the hydrogen can be used for direct energy usage, or it can be used to put into the pipeline to green up some of the natural gas. So these are just some of the options that we see. So I talked a little bit about, yes, nuclear power plants today are flexible, and looking to the future, we're looking at the integrated energy systems with the plants today, and then we're looking even further into the future about how advanced reactors can help with the flexibility, with providing the electricity and some of these other forms of industrial processes that can be provided by the high temperature steam. So I go back and say that, yes, I think it's a match made in heaven. Thank you.
Mark, are you muted?
Sherry, this is Charlie. I don't know what happened to Mark's connection, but let me just follow up with one question about outage rates. Some of the questions coming in seem to indicate that the French fleet has a higher outage rate or more maintenance because of the cycling. than it would without the cycling. Could you speak to that question?
I can speak to a paper that the French have published that actually shows that they have a very minimal impact due to the cycling. They made a paper, they released a public report that is an accumulation of 30 plus years of operating experience that they've had on their plants. And that shows 58 plants, 30 years of experience with that type of cycling. And I think they use the words minimal impacts on the maintenance and maybe about a 2% overall increase in their O&M costs due to the being flexible.
Okay. That's an interesting...
Am I back on, am I? Charlie?
You are, Mark, yes.
Yeah, sorry. Pardon me. Okay. Sorry about that, guys. But another question as well. That was a good question, Charlie. But another question, I'm getting a lot of questions in here about roughly the same thing. One of them in particular, they're saying that the nuclear power plants in France only have an 80% availability in comparison to the US at percent, and they're indicating that availability is because of maintenance, etc., and that's adding a huge cost. Could you? And I know the paper you're talking about, Sherry. It was sent to me a couple of weeks ago. So is that a fair comment that the 80-90% comparison between US and French nukes is because they're cycling, and that adds a huge cost?
The capacity factor will be due to the cycling, but that is because they are flexing. I would hesitate to comment that adds costs to their operations.
Well, I think what it is, the speaker can't speak for themselves, but I would say what it is if they're running at 90%, they're available more often, they're making more money. So maybe that's what the question is talking about, that from an economic point of view. And I think John also alluded to that essentially, that when you build a nuclear power plant from an economic point of view, you really want to run it as often as possible.
I would say it depends on what you're compensated for in your market.
Yeah.
If you are avoiding negative prices, which is in the United States, which started the conversation for a lot of the nuclear power plants in the U.S. to start considering flexible operations, was the negative prices, then that changes the economics.
Yeah.
And you do also have some markets where nuclear power plants or any generator is compensated for availability. That also changes the conversation. Okay.
There's a lot of other questions here, but I think in order to get through the whole agenda, I'll have to keep going. But I'm looking at these questions. I'll try and capture them later on. Okay, thanks, Sherry.
Yep.
Okay, our next speaker is Bethany Frew, who was a colleague of mine until a few days ago at NREL. So Bethany is a senior engineer in the Strategic Energy Analysis Center at NREL. She's got a lot of experience with wholesale markets and power system operations and power system planning. She holds a PhD from Stanford University. Bethany, the floor is yours.
Great. Thanks, Mark. I'm really excited to be part of this panel and presenting on a different topic than I normally do. And so those of you who know me from past ESIG events will recognize that I have a power systems analysis expertise. But this effort that I'll be presenting today, both from a conceptual framing standpoint and also some results from a publicly available analysis document, really reflects a much broader team effort, and I'll talk about that in a minute, that includes experts from the nuclear and the hydrogen perspective. So I want to really build upon some of the content that Sherry has presented, especially as part of this broader conversation about how can nuclear power plants remain economically viable in a low power price world. And at least the work we've been focusing on at NREL, along with our project partners, has been focused on two main approaches. The first of those is to operate the nuclear power plant less during times of low power prices. So this is the point that Sherry just mentioned a minute ago, where you're trying to minimize your losses. So in an area where you're being compensated at a lower price than the cost to operate, it makes sense to turn down. The second point, or second option, is to produce something of higher value during times when power prices are low. And in the case of my presentation today, this something of higher value is hydrogen. And so I'll be talking about how we can potentially hybridize nuclear power plants to produce hydrogen during certain hours of the year. So just a quick acknowledgement about this broader team effort. As I mentioned, there's a lot of folks at NREL. Mark Ruth is the primary lead for these various projects, as well as different project partners, different national laboratories, and key utility partners. I want to call out Southern Company, Exelon, Xcel Energy, and then also EPRI has been a partner in this work as well. Funding has come from the Department of Energy, the Fuel Cell Technologies Office, and the Office of Nuclear Energy, as well as the utility partners mentioned above. So when we talk about hybrid systems, there's obviously a lot of definitions that are floating around out there. So I just want to start with a very traditional definition, in this case, looking at a tightly coupled hybrid energy system. And so this refers to having two or more energy resources as inputs, with two or more products as outputs, where at least one of those products is an energy commodity, such as electricity or transportation fuel. So this figure on the right is an example of one application of this type of tightly coupled hybrid system. In this case, we have a nuclear power plant and a wind generator, and you're producing as your two inputs, and your two outputs are electricity going to the grid, and then thermal output, which can be used for various industrial processes. So we're taking this traditional definition and applying it to a specific instance with a nuclear hydrogen hybrid system. This is a very simple conceptual slide that shows what we mean when we say this nuclear hydrogen hybrid system. So in this case, we have a nuclear power plant that can send electricity as one product to the grid, or it can divert some of its heat and electricity, or just electricity, depending on the electrolysis process, to an electrolyzer to then produce hydrogen that goes to some sort of end use. Sherry highlighted a few of those end uses, and I'll mention a little bit more about that in a couple of slides as well. And so in this case, again, electricity and hydrogen are our two products, but why do we care about hydrogen? Why is this something that we want to focus our efforts on? And it turns out that a non-trivial amount of primary energy use in the United States goes to producing hydrogen, about 2%. And if you look in this Sankey diagram here, you'll notice that the energy that is used to produce hydrogen is coming from natural gas. And so this is mentioned a little bit in the presentations before me, but steam methane reforming is the traditional process that is used to produce hydrogen. And natural gas is the main ingredient for that. So when we're talking about hydrogen, the price for hydrogen is strongly correlated to the price for natural gas. And therefore, when we talk about carbon, it's driven by the natural gas input as well. There's also a lot of growth for hydrogen, and this is really the key part here, that we're able to think about these hybrid systems being able to contribute hydrogen to a growing demand for that product. Some preliminary results shown on this slide indicate that the hydrogen market by 2050 can increase by a factor of over 9. And this is, again, driven by applications from some of the traditional areas, including refining, also ammonia production, that's a big one, but also some newer applications. Again, Sherry mentioned some of this previously, but being able to produce steel, being able to refine biofuels, and also contributing to a broader transportation fuel cell application. And also, Sherry mentioned this too, being able to inject some of the hydrogen into existing natural gas pipelines so that it can contribute to greening up that fuel source. So when we talk about hydrogen production, there are two main processes or options. There's low temperature electrolysis and high temperature electrolysis. Low temperature electrolysis, which is shown on the left, only requires electricity. So you'll see on the bottom left figure that the arrow, the gray arrow going into the low temperature electrolyzer is just electricity. Conversely, high temperature electrolysis on the right side requires both electricity and thermal inputs. And so you'll notice in that figure on the bottom right that there's a gray arrow from electricity and a red arrow from the thermal component. So because low temperature electrolysis is lower temperature, it's lower efficiency, but it also has lower costs and it's more nimble and simpler to integrate. High temperature electrolysis, because it's a higher temperature, is higher efficiency. Currently, it's higher cost, but there's a lot of work being done to try to drive down some of the material costs that go into that process. It's also less nimble. So potential benefits of hybridization, and this is really the crux of why we're doing the work we're doing, is that you can imagine such a hybrid system you can dynamically adjust the overall output of your, in this case, two products, electricity and hydrogen, to be able to maximize the revenues for the overall system. So when electricity prices are high, you maximize your electricity production. When electricity prices are low, you maximize your hydrogen production. And so you can imagine a future where we have a lot of renewables, and this gets back to the focus of this entire session. You have a very high penetration of zero marginal cost resources, and so many hours of the year are low or zero LMPs for your energy prices. And so in that case, you might have this hybrid system that is producing hydrogen for most of those hours that are low prices, and then only a relatively small number of hours it's producing electricity and effectively operating more like a peaking plant. And so this sort of conceptual framing and justification is what led us to the work we're doing now, and we were charged with being able to do maximizing the profitability of such a setup for a specific nuclear power plant that could be converted to this hybrid system. And so with the remaining couple of minutes, I'm just going to talk through an analysis that we, along with the project partners that I mentioned earlier, have conducted, and this is just one example. And so in order to do that profitability analysis, in this case, we're maximizing the net present value, and it's looking across all hours of the year. We first had to come up with some key inputs. And so in the top right corner of this slide, you'll see a hydrogen market assessment component, and this was led by Argonne National Laboratory. And so what they did was they looked at the specific location of this nuclear power plant within a specific radius from that plant to see what the potential hydrogen market would look like. And so they come, they come up with these demand curves that have the price for hydrogen on the vertical axis, so dollars per kilogram, versus the demand on the horizontal axis, in this case, kilograms per day. And you'll notice that there are three different colored lines which represent different natural gas prices because, as I mentioned before, the traditional method for hydrogen production is steam methane reforming, which is based on natural gas as the input. So there's a strong connection between natural gas prices and hydrogen prices. The second main component is electricity price estimation, which is what we did at NREL. This involved capacity expansion modeling to project what the build out for future years at this specific location of this nuclear power plant would be, and then taking those build outs and putting them through a production cost model to estimate the hourly LMPs. And so with the combination of these electricity prices and the hydrogen market estimation were fed into a techno-economic analysis led by Idaho National Laboratory that determined the NPV profitability. And so I just want to take a couple of seconds to talk about this piece that sort of pulled all of this together. And so again, this was looking to maximize the net present value. And there are three main dimensions of this analysis, again, looking at all hours of the year, and that's shown in the figure on the right. And so those dimensions are the hydrogen market size, which is the vertical axis, the hydrogen storage capacity, which is the axis that's going in and out of the screen, and then the electrolyzer size, which in this case was a high temperature steam electrolyzer, which is on the horizontal axis. And so the profitability really depends on a lot of factors. There's a lot of interdependencies that happen here. It's very location specific. And so some of the key levers that we found in this work is that profitability depends on the relationship between hydrogen and electricity market prices. So if electricity market prices are really low, then it makes a lot of sense to produce hydrogen. If prices are very high, then it might not make sense at all, and you're better off maximizing your output in the energy market, the electricity market. It also depends on the size of the electrolyzer versus the hydrogen demand, and also the size of the hydrogen storage. The electrolyzer and storage are capital intensive items, and so if you oversize those and you aren't able to have sufficient utilization, you're basically wasting capital. So the key finding, and this is what I want to leave you all with, is that nuclear power plants with regional demands for hydrogen, so in other words, again, it depends on the location, have the potential to increase their profit margins by hybridization with hydrogen production. Again, a lot of details are involved with this, but there is the potential. So I'll wrap up there and we'll open up for any questions.
Okay, thank you, Bethany. And again, there's a lot of questions here. I'm going to try and roll some of them together. There's been several comments made about the fact that electrolysis needs to be run 24/7 to make it economic, and the same is actually true for nuclear power plants. So is what you're proposing, does it is it playing to that? Is it trying to, I mean, does the electrolysis run 24/7? Maybe not by nuclear, but by other means. Is that correct?
At least in the configuration that we've been evaluating, the nuclear power plant is running 24/7, so it's running at full speed. It's basically, and if I'm maybe using layman's terms here, but you're effectively throttling between electricity maximization or hydrogen maximization. So you still have the same amount of steam and electricity. It's just whether that is diverted to, well, assuming you have a high temperature electrolyzer, it's whether you divert some of that to the electrolyzer or if you're sending it all through to the grid through the reactor.
But
I can't speak to the. Yeah, at least in the work we've done, we haven't been assuming that the electrolyzer is running 24/7.
Okay.
I think there's a lot of options, and this is where Idaho has taken the lead of sort of optimizing the electrolyzer size and operation. So I might want to let others who are more knowledgeable on that speak to that point.
So maybe we'll just leave it there, but maybe it's a case that the electrolyzer may be uneconomic in that case, but we'll see. We'll let others answer that question. There's another few questions about geothermal. Would have we looked at actually, I mean, I'll just read it out. Given the difficulties inside the nuclear plants and in legal prohibitions, waste storage, could geothermal power perform all the hydrogen production functions you're discussing?
I can't answer that definitively, but I mean, given that there's a steam component and electricity output, it seems that could work. Again, it all is driven by the economics, and I think this touches on the first question as well. It really just depends on sort of the trade-off between your electricity price and your hydrogen price and what you're being compensated for to determine which option is better. And so, it would depend on the economics of the geothermal plant and the location and the potential hydrogen market that's available at that location.
Okay, and one simple one. Is there a CO2 price in this story? Is there a CO2 price in the analysis? In
this particular example I showed, we did not, but there's other ongoing work we have that we are, and the way we've included it, at least on the NREL side, because again, we're focusing on the electricity price piece that feeds into this broader work, is that the carbon price would effectively increase the LMP. For at least for the hours where those carbon emitting resources are on the margin and setting the price.
Okay, so listen, I'm going to some of the questions that are coming in from people are great. Keep them coming. I'm going to use them at the end because I think we'll have some time for discussion at the end. Okay, thank you, Bethany. A round of applause by everybody. You can hear it in the background. There you go.
Okay, thanks, Mark.
Okay. So our next speaker is Nikhil Kumar from Intertek. So Nikhil is the Managing Director of Intertek's Engineering and Digital Solutions business. He's an expert in power plant cost analysis, generation reliability, risk assessment, and economic analysis. He serves on the ASME RAM committee. I presume ASME is the Society of Mechanical Engineers. AWEA, which is the American Wind Energy Association, I assume. O&M committee, and is a senior grid integration advisor for USAID Greening the Grid initiative in India. Nikhil, the floor is yours.
Thank you so much, and thanks everybody for joining. So hopefully with my slides, which I'll go through very quickly as Mark's reminded me, is we'll probably maybe get a balanced answer to John's presentation and Sherry's presentation, where I think in the end it comes down to economics at the site. Also, I'm hoping we get a lot of hydrogen. As somebody who drove a fuel cell car for 3 years, I really hope that the hydrogen prices fall a little bit. It's about $16 a kilogram here in California. So with that, I'll get started. As a quick introduction, I think if you look at the U.S. fleet, there is a case to be made that we have an aging nuclear fleet, and we'll talk a little bit about France and Germany. Well, I mean, the case of Germany, they're mostly at the end of their nuclear operations. They're going to be shutting down most of their units, so it's really the French case and then the U.S. case, which has a much aging fleet. So today, when we operate these nuclear plants, there's a lot of O&M, as John probably alluded to, and a lot of it is associated with safety, life cycle cost management, aging management, and risk mitigation of the equipment. But as we go ahead into the next several years of operation, I think long-term operation, which is key in the U.S., the NRC in the U.S. gives licenses for 40 years and with 20-year extensions. In the U.S., almost all of our nuclear units have been extended to 60 years. of operation, and some have applied for an 80-year extension. So long-term operation certainly is part of the equation. And then I think flexible generation will become part of the equation for these operators. So we are obviously looking for grid flexibility and increased renewables, but I think part of the discussion is having to operate these nuclear units safely. If you go to a nuclear site, I think the number one motto there is safety. Reliability, I think, obviously, but then to some extent cost recovery, because if in the French case you increase the price, the cost of generation by 2%, if you look at the paper, then already nuclear is not all that cheap to operate, and I'll show you that, especially if you don't operate it baseloaded. So similar to what Sherry said, most existing plants actually are already designed to respond to some amount of load change, and you can do that without tripping the reactor. And the other case is, and this is not common. You need to get regulatory requirements met, safety requirements met. There's a number of cases in that, but you can actually reduce the thermal efficiency of a nuclear unit by dumping that steam into the condenser. So there are certain mechanisms available to units today without doing a lot of operational changes or a lot of extra O&M or retrofits to make them flexible. So I won't talk so much about baseload operation or frequency control. Let's talk a little bit deeper about load following, because when we talk about flexible nuclear generation, maybe the SMR design, newer designs will be able to do more than load following. But in today's scenario, let's just focus on load following. So quickly, what we're talking about is megawatt changes up and down, not turning off the entire unit. There are certain ramping constraints for this. There are obviously some minimum load requirements here. So even the French units have, not all units go down to 10% or 15% low load. There are certain limitations to minimum load. There is some equipment damage. There are also fuel cycle limitations to some of these units. So, I think Sherry mentioned the PWR units. As you get into the latter part of the fuel cycle, even the French operators minimize the flexible operation on those units depending on the health of the system that they have, economics and obviously cost. So that's really what I'll focus on. And here's the German case. So, if you look at this, it says grid requirements in the 1990s, 1992. So, the blue lines here show what the grid requirements were back in the 90s, and they were considered in the safety analysis and establishing the design limits, which are in the red. And they actually included flexible operation back then in the 90s. So they've actually been expanding some of these limits even today, well, for however many more years they operate. But this was part of the design mechanism for the German PWRs. In the US, we haven't quite done that. French obviously do that. But if you look at that table, when you get the slides, and you can see that in more detail, that there were quite a lot of cycles allowed within the design framework of these units to operate safely. So that's just one example. And then this is actually the Bruce Power operation, which is in blue. And you can see that, this is a little bit old. I was trying to look at more recent operation with this flexible generation, and it's actually minimized a little bit. It could be because of, some other reasons that I'm not entirely sure of at this point. But a couple of years ago, we could clearly see a lot more movement for Bruce Power over the day and over the week as it operated flexibly. So units are, as Sherry said, operating in some amount of flexible generation already. And before we get to the economics of running or cost recovery of flexible generation, let's just see what's happening already in the US. The market is actually the big driver for a lot of closures. So 11 gigawatt of capacity of nuclear units is about to retire by 2025. Half of the units operate in deregulated markets. So there is a lot of pressure from the market. But the big problem here in my world is that the operating costs are the major drivers of why they're not in the market when they're operating. And when you look at it from an O&M standpoint, the nuclear units, both from an operations standpoint as well as maintenance standpoint, are far more expensive than the conventional fossil fleets. And so, we have been making efforts to reduce that over time. So when you look at this chart, you could see that in the past, from 2002 till about 2012, we saw a steady increase in cost for nuclear units. And this was a lot to do with relicensing and uprates and all of that. But there has been a lot of effort on the part of nuclear units to reduce that cost. So we're seeing an encouraging trend of reduced O&M, which hopefully into the future will help them make some of that operating in deregulated markets a little bit more profitable. So when we look at nuclear flexibility, we need to take into account the range of operation, the duration of low load operation, and the ramp rates. I'll talk a little bit about ramp rates in the coming slides, but there are a number of things that we need to take into account as we operate these units flexibly. So I'll leave it at that and keep going with this. So again, on the left-hand side, these are all on the y-axis are log scale. What I said was the average non-fuel O&M dollars per megawatt hour has been trending down. It went up a little bit in the early 2005 through 10 period, and then it since then has gone down. So this is all encouraging from the standpoint of costs. Now, we show this slide on a number of our work for a conventional fleet, and I want to remind why that power plant is upset there. It's upset not because you're operating it in a flexible mode. It's upset because it doesn't get cost recovery for the increased damage that it incurs from flexible generation. So, I think there are a lot of experts on this panel that can talk individually about each of these blocks. But fuel management, vintage, aging mechanisms, mode of operation, fuel cycles, time between outages. There's a lot of variables that come into the play when we talk about flexible generation costs. And what you have to do is really come down to individual. If you want to see a safety case for a nuclear unit, it can run into hundreds and thousands of pages looking at every single component, looking at their fatigue, life, consumption. So there's a lot of work that needs to be done. I know EPRI is doing a lot of it. Individual units are doing it. EDF has published some really good papers on this. But there's a lot of work still needs to be done to quantify how much of this fatigue life consumption occurs as you operate these units in cycling mode. And, it's not just happening on the nuclear side, the excess damage that we talk about on these units, the electrical controls, the generators, the conventional part of the nuclear unit, the steam turbine, all of them get impacted as you operate these units in flexible mode. So the 2% increase in O&M isn't out of the realm of what is possible. In some cases, when we've studied these accounts for US units, for example, they're not even as high as 2%, in some cases less than 2%, but we have seen some units where the O&M expense may go over that 2% level. So 2% is probably a good approximation to start with. So we have been developing a number of methods to actually quantify what will this excess cost be as you operate these units in flexible mode. The auxiliary power costs do go up if you operate these units in flexible operation. This is particularly in the case of nuclear units. And the fuel is another big area for us to consider. So when we study, this is, for example, for a BWR unit, when you look at the total system, you're trying to look for what are candidate costs? What are some of the costs that can or will get impacted by flexible generation? So this is just a snapshot of what is possible. And like I said, fuel is a big part of it. The condensate system is next. But this is just as an illustration for you all to sort of see where these costs can come from. And I want to again say this is illustration only, but let me talk about this little line that you see in the middle of this chart. What I'm showing you there is the dollar per megawatt capacity of load following costs for a nuclear unit. That's a big range. It is anywhere from a few cents per megawatt change to almost $6 per megawatt capacity. And it really comes down to the specific unit, but also the level of load changes that you're going through on these units, and where you are on the fuel cycle. So it's a big, broad range. But I put a little a dot close to that $1 per megawatt capacity, which if you look at most units that Sherry's been talking about in North America, if you look at the load changes that those units are performing, that would be a reasonable approximation. And if you do a back of the envelope calculation, it would come down to that 2% cost. But I wanted to give you that scatter band of, that it's not that simple that, we pick a number there and it'll give us the total cost of running these units in flexible mode. So there is a lot of scatter. Each cycle has its own damage mechanism. Your pumps, your feed water heaters will behave differently versus your steam turbine or the primary circuit. So there are certain constraints, certain limitations to this analysis, but we just wanted to give you sort of a range of what this cost looks like from a load following standpoint. If you're familiar with our work for the conventional fleet, that dollar per megawatt capacity for load following is actually very competitive, or actually lower than some of the conventional fleet. If you look at a supercritical cold unit or a subcritical cold unit, they run at a much higher temperature and pressure than a nuclear unit. So in terms of load following, the cost for nuclear units to do so is not that much more expensive than the conventional fleet. And I'll finally give a shout out to a report that the IAEA published, and Dr. Kilich was one of the lead authors on that. But if you want, you can click on this link, and there's a lot of good discussion on some of the constraints of this flexible operation. So that I'll end my talk here.
Hello, Mark. Are you on mute?
Yes,
we lost.
I'm on mute.
Oh.
Sorry.
Okay, we lost.
So I was speaking to myself there. Okay, thanks, Nikhil. So a couple of questions for you. So going forward, are these costly engineering issues that need to be addressed to provide flexibility in new plants? So, talk about new plants, Nikhil. Is this, if we were to build new ones, you're looking at existing plants, I assume. What about new plants?
Right. I think the next presenter can talk far more in detail on newer plants. No, absolutely. I mean, to me, the cost might go down, but I think as far as it's in the design case and you meet the the safety concerns and the regulatory concerns, I didn't talk so much about this, but if you go back to some of the slides, the regulatory costs, at least in the U.S., is significant. It's not, it's not a trivial amount. So there are a lot of costs in operating nuclear units in the U.S. that are not directly related to O&M as we speak in terms of megawatt hour generation. So certainly in the future, we do have an opportunity to reduce those costs and make them more flexible.
Okay, and another question here about the fuel cycle. I mean, you did mention yourself that these costs are somewhat determined by where in the fuel cycle you are. Is that correct? Is that what I heard?
Yes. Yes, especially in the PWRs, yes.
Okay, so it's a very variable thing. It's not a fixed number. As the fuel in different parts of the fuel cycle, these costs get dramatically different. Is that correct?
Yes, there is a bit of a spread there, and it's not so much the cost increases particularly. for example, the French case, they just minimize the amount of flexible operation. They run a fleet of units, right? So we're not talking about a single unit. So they minimize the flexible generation from that unit for various safety and physical reasons on the unit itself. There are certain damage mechanisms that they're trying to avoid. So, and there's a lot of research that EPRI's done and others have done that minimize that effect, but that's just a physical constraint of operating the unit deeper into the fuel cycle.
Okay. And the physical, but you also just said there a while ago, so is the regulatory issues, is that adding, I don't want to put you on the spot, but in terms of cycling and the regulatory issues, I mean, is it 10% of these extra costs come for the regulatory issues, or is it 50%? I mean, you seem to indicate they're significant.
Yeah, I don't, yeah, like I said, I don't think I want to get into a spot there. I think each site would have its own concern there, but it is a part of the equation here. And there are limitations. You know, you can't just take a unit in the U.S. at least. Internationally, it might be a different case, but you can't just take a unit and start operating it in a flexible mode without going back to the NRC and proving that it is okay to do so.
Okay. There was a question earlier on, I'll bring it up now as well with you, and maybe someone else wants to answer it too. But somebody asked, you know, if these units are being, do these units get controlled directly by the control room? So, you know, when the system operator wants them to do something, or because they're nuclear, do they have to sort of ask someone in the control room to do it? So how operational are they in terms of making them do things?
Yeah, I think this question's come in the past as well. And I think Sherry might be able to answer this and confirm my thought here. But I don't believe that in the US we can just change load from grid. Units have to airwin.
Yeah. Okay. So that's another sort of hurdle to come over. So we will leave that one sit. And Sherry, if you're still on the line, you can answer that later. Okay. Thanks, Nikhil. Very good. Okay. Our last speaker then is George Griffin from INL. So George is a system integration manager at INL, where he's a small modular reactor lead. His current work is focusing on siting new reactors and enabling technology. He's had past experience with Cooper Nuclear Station, so he's been out there in the real world, so to speak. And he's our only speaker to hold a PhD in nuclear engineering. So in many ways, we've been speaking about something we know nothing about. George knows all about it. All right, George. Okay,
yeah,
George.
Thank you for the Thank you for the introduction. I've certainly been enjoying the conversation. I feel like I'm about 6 feet away from all these topics. As we get into it, I want to acknowledge that Connor Frick is one of my staff members who did a lot of the modeling here, and somewhere in the silent audience is Shannon Bragg-Sitton, who's an expert at the integrated energy systems. So some additional capability at INL that I'm representing. To start out, this is a picture of a small modular reactor as it would be shipped. They're planning to build one of these at INL as a commercial venture. And this is the largest component of the actual reactor that would go into the function as the core. So when we say small, these are still significant engineering tools and designs. For reference, we talked about small as well and large. The scale up on the upper right shows a range from the current sort of modern submarine core, which is the small end of the scale for practical reactors right now. We're looking to make those much smaller going forward, all the way up to the EPR at 1,500, some proposals for 1,800 megawatts, where these things are becoming national strategic assets. And SMRs are at about 60 megawatts each, and so it's a relatively small unit in and of itself, and the intent is to build 12 of them at a time and get up to sort of the gigawatt size reactors. So that's the SMR. What makes a SMR unique, particularly the NuScale design and some of the other forward-thinking ones, are that they're integrated. This is the NuScale module to the left there in gray. The little tiny block is the core. It's about 6 feet high and about 6 feet in diameter, and sits at the bottom of essentially a giant thermos. And the upper portion of that is what was shown on the graphic on the front page, the top part of that thermos. And what's really interesting is they have managed to take all the components of a conventional PWR and squeeze it inside that vessel. The upper right picture there is a conventional look at a Westinghouse style PWR. You've got steam generators, external pumps, pressurizers, all of those components, their piping, their valves, the instrumentation, all of that has been squeezed down and simplified to go inside of one of these modern reactors. And so the NuScale reactor in particular was designed to address a lot of the issues you guys have been talking about. What's the maintenance look like? Well, an easy way to get rid of maintenance is to get rid of parts. One way to get rid of engineering is to get rid of complexity. So these reactors have been very much designed to address the grid that was pictured. And the design process for this was almost 20 years ago, but the reactor design itself seems to be well suited to the sort of problems that we've been discussing. So an interesting benefit there. So for a single unit, that big thermos on the truck, this would be one of them, 60 megawatts electric. It's a conventional PWR, so 28 to 33% efficiency. They give up some of the efficiency on that, the high temperatures, to be conventional, to not take technical risks, to make the NRC licensing easier. There are a number of advanced designs that are much higher temperature. They engage with technical risk and NRC questions and difficulties with licensing as first of a kind. So these reactors are designed to go through the licensing process as well. You can see they're about 3 meters in diameter, 20 meters high. And the staff at one of these plants is going to be about 365 as compared to about 800 at a standard single unit plant in the US. And the picture shows the very large container of water, the pool that each of these reactors will go in. And the standard design right now is to put 6 reactors in their bays on the left side there. The right side is used for incoming units, for maintenance, for refueling. And the left side is the 12 units to produce power. In this design, each unit gets its own turbine and condenser and power generation system. So as we'll get into it, that shows some flexibility that's inherent there that you don't get from a single shaft on a gigawatt machine. And as part of the systems work that we have at INL that's shared with NREL and others, we've been building a model of this particular type of reactor. So that's the graphic on the left, built in Modelica, the core at the very bottom again, and all the steam generation equipment up above that in the reactor. And so by building component models, these can be hooked together, putting the right attributes on the way they're connected, the way they interact. You build an accurate model of the reactor system. And here it's blown up a little bit. You get steam manifolds there as a component, so you know how the steam travels out to the turbine and back, a turbine model in and of itself, a line break, and then in this case an infinite grid, so someplace to take the power off of. A large amount of detail can be and is being built into these systems. All the way down to, we're talking about, you know, what are your licensing restrictions? What are your performance restrictions? We have the model built so that it can actually keep track of thermal limits. You know, you can't operate your reactor so it's too hot or in a condition where it might be dangerous. And that's all managed through the license and the NRC application process. So this model actually gets down to those level of details, things that are interesting from this engineering standpoint, like fuel center lines, bulk fluid temperatures, things that you need to monitor in a real plant, makes this more realistic. So we're trying to address some of the questions that have popped up here. Details on the pressurizer and how you heat and cool that to maintain reactor control, and the details in our particular model on how do you change power? Do you move the control rods? Is it flow related? Other sorts of issues are all modeled in detail. And so we started out to build a replica of the NuScale unit based on what they have submitted to the NRC. The NRC design process or review process is largely public, so they provide information that can be reviewed, can be seen. We can use that information to build our models. And so this is for the 50 megawatt example here. That was the original licensing level. To cut costs down into the $60 per megawatt range, they have upped the power per unit to 60 megawatts. That's part of the negotiation with the future owner-operator for exactly what they want. And as you go forward, we're seeing results where the steam generator pressure remains the same as it must. Turbine output matches the turbine demand. We get flow rates that are very close to what we would anticipate. and temperatures and pressures are maintained within the design limits as we know them. So it's a model that's showing accuracy to what's publicly available. And so into the load follow, which I think is probably one of the more interesting parts of all of this. Despite being designed 20 years ago, it's a flexible tool that seems designed to work in our modern environment. In particular, when we model it, we can see turbine demand over 24 hours works. You can match demand without control actions are all within specifications and availabilities. Temperatures, pressures, powers are all at safe levels. The graph with the large red line on it shows some load following modeling being done. And you go into the literature and you can find where NuScale has designed this reactor to go from 100% to 20% back to 100 within 24 hours. Similar maybe to what the French are doing, even more extreme than that. The reactor can manage a 40% ramp rate. Obviously can't do that continuously up and down. That would be bad for the plant, but to respond to transients, the reactor is capable of moving at that high rate. You could do 20% step in minutes. And this is all at the reactor power levels. So one reactor can do these actions. Now, the picture we had 12 units online on the plant. If you were looking forward into the future and you knew that you were going to be operating like Columbia Generating Station at 70% power, and you knew that that was going to go for 3 months, you might well take 4 units offline and then run the plant as an 8-unit plant at full power. And the 4 units would idle away in a shutdown mode and save their fuel costs. And then you would start them up when the demand came back. So some flexibility just by being a modular plant in this case. And then maybe the ace in their pocket for this particular design is because the plants are individually smaller and they have smaller turbine power generator sets, they're able to completely bypass steam into the condenser. So as fast as you can open and close the throttle valve, you can shift power from the turbine into the condenser. And so if you need to drop power very quickly to the grid, you can take power away from the turbine, dump it to the condenser. Reactor power stays the same. You don't run into thermal limits or operator actions that might affect the core excessively. So it's a very useful flexibility. And then this is where the integrated energy system comes in. If I build that train, whether it's hydrogen, desalinated water, or something else, when I go to bypass, instead of dumping it to the condenser, it could go to that secondary train and make the high value products needed. So some flexibility that shows up that wasn't intended, but proving to have some real benefits, at least as the thought experiment on how to make these units more effective. And then one note I found was that this does meet the California power duct curve. The nuclear power plant as a whole can respond to that daily ramp and operate continuously. And if you knew you were going to do that, you would build that into the license. The capacity factors would match, issues of control would all be modeled into that and approved. So that could be done. So conclusions, NuScale is an advanced design. It addresses issues with deploying the reactors. Since they're individually smaller, they're easier to build, more economic to build. They're simpler to operate. They're simpler to provide the engineering for. These reactors can operate in different modes with different reactors online, different power levels, and different amounts of bypass, making them very flexible on the grid. The NuScale sees them addressing different markets, all the way from replacing small coal plants with dual units up to the full-size 12 module units. And we're seeing that the detailed model can be made, that the response is correct, and that the units actually do perform as expected. And we look to integrate these with more other sophisticated models to actually show how the reactor would perform with a hydrogen system, with wind energy, with other energy storage options. So we're working toward demonstrating sort of the future we've been talking about. And wrap it up there for questions, I think.
Okay, George, very good. I've got several questions for you here. First of all, people want to know when. When will this be deployed? You're building a demonstration. When?
Yeah, the NuScale built a very sophisticated thermal hydraulic model in Oregon at the university. and they have used that to get through their licensing in a very linear and expected way. And they expect to have their license here in the next couple of years. The plant is currently, the first unit will be on the Idaho National Laboratory site, be a commercial operation. It'll start up sometime in the late 20s. I think the final date on that is become a little grayer as they look at all the activities they have to do, but the late 20s. And then they're factory built, so they'll be able to fill any demand that comes in behind that.
And then any idea of the levelized cost of energy? Is that a hard question to ask? Or, yeah.
Yeah, well, and it's interesting because it's one that we at least have some insight into. The potential owner-operator is the Utah Association of Municipal Power Supplies, and their stated goal is they would like to be at 60 megawatts per $60 per megawatt, and that's the target. And they're willing to go a little higher than that because of the some delivery costs that they have with natural gas. But it's a direct competition with natural gas in their minds, and that's the one that's being looked to meet. So they're in that $60 a megawatt range.
So that is substantially cheaper than existing pressurized, the existing technology. Is that correct? So
correct, and it's
now, yeah. So
yeah,
this is one of those breakthroughs that someone else asked earlier. So you think this technology will actually bring the cost down substantially?
I think so. The tool was actually built to be a low-cost producer, at least for nuclear. And it's the difference between, do you have a full-size pickup? Well, that hauls farm goods and street stuff and does work. Well, if I wanted the most efficient version, I'd buy a Prius that gets really great gas mileage. The two designs, different times, different intents. This reactor is intended to be a low-cost unit. It looks like it will achieve that. Okay,
this is a very technical question, and from an ex-nuclear submarine person, as far as I know. There's much talk about benefits of liquid fluoride thorium reactors and use in small reactors. What's your view of the trade-offs with pressurized water reactors?
Yeah, I guess the way I think of it is in the future, there will undoubtedly be places for more advanced reactors. This presentation is very focused on NuScale because it's near term, and that defines what it is. In the near term, what we're going to have is PWRs and BWRs, variations on that. As we go forward in the next 10 to 15 years, I think we'll get higher temperature gas-cooled reactors, molten salt reactors, possibly fast reactors. The molten salt reactors in particular are interesting because they're potentially very high temperature, very safe. They offer a really very interesting option for modern reactor designs. And I think the molten salt is appealing for that. You could potentially lower the costs even more, be more efficient. They would match very well up with hydrogen production or working at oil facilities. The question is, well, now to do something completely new, you've added regulatory risk, you've added technical risk. Those things will take a little while to work out. PWRs are a very mature technology. We're comfortable with it. So I think there's at least niche markets that open up first, and then as we go forward, as they prove their benefits, you'll get more of those designs.
Okay, I'm going to wrap up those questions for you, George, because we have a few more minutes left here. So I just want to ask all the panelists who are on, does anyone who's on the panel, because some of these questions have sort of, Sherry, for example, your name came up earlier. Does any of the panelists want to chip in with a comment now to sort of back up some of the answers or make some comments? I don't hear any volunteers. Okay, there is one question here that I think is a generic question. It's a question coming in. Is it fair to say that one of the reasons that these plants are cycling is simply because there's sunk cost? They're there, they're having to do it, and we'll all look at cycling. But that if we were to build them new, we wouldn't cycle. The only reason they're cycling is because they're there now, and that is not the ideal option. That the only reason they're doing it is because of necessity. Anyone want to answer that?
So this is John Reilly. I can take a crack at that. I mean, that's essentially what our paper would be concluding, looking to the future, that if you are building a reactor, you'd like to operate it almost, as much as, all the time, and except for, maintenance that you need to do. because that would give you the lowest levelized cost. Otherwise, you just have capital sitting there. So the plants, but of course, we can't, we never plan exactly, and the world we're in today is one that no one really thought about when these nuclear reactors were being built. So they are now wanting to cycle, and if they can technically cycle, they will, and that can at least produce, power in some other situations. Again, the decision then to relicense them or to, which would require another investment as another investment decision about whether, given the investment and other costs of operating, does it make sense to then relicense them again? So, so I think my answer would be, if you're going to build a reactor, you'd like to operate it 95% of the time. So that's what you're kind of planning to do. Anything less is kind of a disappointment. But and then the question becomes, how does that cycling compare to the other possible options that many people brought up?
Okay. Anyone else want to make any more comments? We're just nearly out of time. So I'll just make a few observations before we wrap up about this session. I found it fascinating. I'm very pleased we had it. I have to say, I don't think we've answered the question. I think the only person who answered it was Sherry, who said that she definitely thinks they're a match. There seems to be a lot of unknowns here still, though, and maybe we should run another session on this, because it's not clear to me from what I've just heard that this, there's no clear answer to this for sure. It seems as if there's still some debate to be had. I think the last speaker holds out some great hope that we will have actually cheaper nuclear power plants that are built for this. I think that's very, very interesting. The cost of cycling is clearly not simple. It's clearly a complicated issue. The hybrid solutions, I think, are very, very interesting, because I think that's part, but I think we need to have the whole story. When you get into hybrid solutions, you get into other technologies, etc. I think, though, fundamentally, though, one thing John said earlier, I think is true. Nuclear right now is too expensive. I think that we, on a levelized cost of energy basis, and I think that's part of the reason that it's having a bit of problem in the marketplace. And it's very clear that the regulatory issues are adding to their burden for sure. So I can't really make any great conclusions out of this. I just think it was worthwhile. I'd like to thank all the speakers. I've learned a lot. I think we should go further. I'd ask the speakers to look at the questions, because there's a lot of really, really good questions in there that I didn't get to. So Charlie, so that's the end of the session. So Charlie also asked me to wrap up the entire conference. I did this at the last conference in Albuquerque, and it was great fun, because I had I think it was 7 gentlemen sitting in front of me who I also told to sit on the stage, and then I embarrassed them. So anyone who's at it can remember that. The only problem with doing it online is that you can't have jokes like that. So I'd wrap it up and say I would like to be with you all again, because in person you can have a lot more fun than you can on the end of a telephone line. I think it's been very interesting, though. I think it's been very useful. And thank you very much. I'm finished. Hello?